talk today is Professor Philippe Jaming from the Bordeaux University, Université de Bordeaux. Here, so you.
Yes, thank you. I would like to thank the organizers to give me the opportunity to speak in this prestigious place. And I will start my talk with a triple apology. The first one is that usually I try to mention a mathematician from the country I'm speaking in. And after having given 8 talks about the Littlewood conjecture, I decided to change subject. So my only citation will be Hardy, who praised himself on being a totally unapplicable mathematician, and in that aspect I failed less than he did. So there will be no application, no real-world application.
Excuse me, but in the title you mentioned Donoho Logan.
Yes, you will see. But Donoho Logan is applicable, I am not. I will mention Donoho Logan. I didn't change subject.
I didn't inform people about the title, sorry.
Okay. So that was one apology. The second apology is that being French after July 14th, I stopped doing any serious mathematics. And I will make no exception today. And the third one is that you've seen I use stroke. That's because I just submitted a grant and I had to say how I will save the environment, and I said I switch off the computer. Okay, so what is large C? Before this, the most important part is that what I will speak about is joint work with Anton Baranoff from St. Petersburg, Karin Kelly, who is also in Bordeaux, and Michael Speckbacher, who was in Bordeaux at the start of this work and has back to Vienna since then. So what is the large sieve? Which is one part of the title. The classical one is maybe the following thing. We should start with this.
Excuse me, but in the title there is no large sieve.
There's no large sieve.
The title, it was my fault.
So I did change the title.
Oversampling.
Don't worry,
Donoho Logan type theorem in model space.
So it's Donoho Logan large sieve type theorem. No, I cut the title because for some reason my PDF was not copying, pasting, and so I retyped a part of it and made it, because I'm a lazy guy. As you see, I didn't prepare slides, I used chalk, etc. So the Donoho Logan which I'm going to speak about is Donoho Logan's large sieve theorem, which is, before this, I give the traditional large sieve theorem, which is the following. Not mess up too much with notations. So I take a measure on 0, 1. It's an L2 theorem. There also exist other LP theorems. And the L2 theorem, this one should be Montgomery, who attributes it to Bombieri. And I think there are earlier versions, but that is the one with the best constants. So n is the degree of these polynomials. These are complex numbers. Delta is a positive number. And mu is a positive measure. And what you will have is a measure of 0, 1, understood as being, everything is periodic, of course, of x plus delta, and then you have to normalize everything. So it's usually stated with m plus n, so it's an n-term piece of a Fourier series, actually. So this is the traditional inequality, has been used in compressed sensing as well. I don't remember by who, maybe Joel Trop. Okay, and there are various ways then to see statistics.
It goes to Liebig first.
Yeah, possible. The one I'm stating is really Montgomery Bombieri with the constants. Okay. Let me give two examples.
And this is what, for any delta? Yeah, delta.
For any delta positive. If you take Dirac masses, then delta will be the separation. And let me call this guy here P of t to make it faster. Then what you have here is just sum from j equals 1 to n of p of xj squared is less than this thing here. This is just this is just 1 in this case, times, and this is the L2 norm of P. Okay, so it's part of a Marcinkiewicz inequality. If I listened perfectly this morning, only the second inequality.
But you should divide it over n.
Yeah, 1 over n. And if I take a measure like this, with t such that, what do I want to say? For all x, t intersects an interval of length 1 over n, so the number of the degree of the polynomial only in a fraction epsilon over n, then you would have this. Okay, so you have these inequalities. They are perhaps more interesting with the complementary.
It's mu there.
No, there's no mu. Mu is 1 t dx.
But there's, okay.
If I take a mu that is just a restriction of the Fourier, of the Lebesgue measure to some sets, then I get something like this, if this set satisfies this sparsity constraint. Okay, and I promise Donoho Logan. Donoho Logan is the extension of this from trigonometric polynomial to their cousins, band-limited functions. Okay. So I need just to recall you what the Pellegrino space is. It's the set of all functions in L2 of R. It's one-dimensional. There exist higher-dimensional results, but for me everything will be one-dimensional, and the support of the Fourier transform is included in minus omega. Okay? And then Donoho Logan is the following result. So here I'm integrating on R. The L2 norm with respect to the measure mu is bounded by some constant which is very small. It's 1 point something. And I don't remember what the optimal one is. And it's not really what I'm interested in. Delta supremum of R, or should I write X, of the measure of an interval of length delta over the Lebesgue measure. Okay, I write it on purpose to make it look at the density. This is, of course, a way to write delta, but it's just a ratio of how much the measure mu charges this interval over how much the Lebesgue measure charges this interval. And here you just have the Lebesgue measure. And then Donoho, Logan, they were applied mathematicians, real ones, not like me. And they applied it to signal recovery from missing data under the assumption that you're in a Palevino space. And it's basically probably one of the historic building blocks of whatever is sparsity methods.
How does it depend on omega, this result?
Why is omega? Okay, and okay, every talk should contain a proof. So I will give you a hint of proof to explain why we have been looking for another one. And the proof goes as this. It's two-step. Step one, you assume that there exists a function g, and step two is I construct g, but I will not give step two, I will just tell you where it comes from. Such that is supported in the interval minus delta over 2, delta over 2, and such that the convolution operator is invertible on PW. Okay. And then what I will take is a thing I call F star, just a notation. It's not the complex conjugate like sometimes in signal processing. Well, if Tg is invertible, I can write this object. In other words, F is F star conjugate of G, whichever order I write it. Just notice that because I will use it, the L2 norm of this is the L2 norm of its Fourier transform. I square it because it's nicer. But this is what? It's f hat over g hat. It cannot be anything else. So it is less than the supremum of 1 over g hat of psi squared, f hat squared, but with second Parseval, I go back. Okay, I didn't say where I put 2 pi's, it doesn't matter, I use twice Parseval, I come back. Okay, so 2 pi is equal to 1 in this talk, squared. And there's just a little thing that is important here, is that f is in the Palevino space, so this is only over minus omega omega. Okay, so I don't need g hat to be non-negative, to be positive, I just need it to be g hat squared. I just need this not to vanish on minus omega omega. So there are plenty of g's you can take for which this will be the case. And the construction then in step 2 is to find the best g, and this I will not give. It's based on a construction of Berling of a band-limited function that majorizes the sine function, from which you construct one that majorizes a characteristic set of a function. And that is the one that will give you this nice constant with roughly 1. Okay? And then how do I conclude? From there, then I just write the following. This thing is, of course, f hat conjugate of g. I have to square it. I write what this thing is. It's integral of minus delta over 2 delta over 2 g of y, f hat of x minus y. That one here is nice. That one here is not so nice. So Cauchy-Schwarz gives me that I have integral of what? On one hand, I have g of y squared, dy. And on the other, that's why I have to be careful, I will have integral of x minus delta over 2 x plus delta over 2 f hat of x minus y squared d mu of x. That one here goes out of this integral. And for the other two, I invert them. So this is the L2 norm squared of g. And for the other two, when I invert it, I will have f hat, call this thing here t, squared. And then I will have integral of t minus x over 2, t plus x over 2, d mu of t. Oops. Delta over 2, delta over 2. Which one is best? That one is t, that one is x, dt. And this one is precisely less than. Minus delta over 2t plus delta. That's it. And this one, we use this. So you get a constant, and then by choosing properly g, you get that. Okay? So now, what is nice with this? It's nice, it gives the best known result. What is not nice, it depends very, very strongly on the Palevino space. Meaning that we use, okay, definition, we use that we have convolution, and we use that we have a very nice function that is constructed through special functions. Okay. So if we want to leave a little bit of Palevino space, it becomes much more difficult to get such a result. It's still a possible strategy. It's one thing started, I think, mainly by Daniele Abreu, I never knew, and Michael in Vienna. So there is some flexibility that allows to do it, but in some other circumstances, it's just not possible. You don't have enough tools. So you want to replace them, and then you ask, do we have other features in the Palevino space that are applicable? And that can then be expanded. So if you think of Palevino space, what are the key features of Palevino space? Okay, there is convolution, that's one thing, but this definition from the Fourier transform, but the next thing you may think of, if you have had any course in which there is a chapter on the Palevino space, you would have Bernstein's inequality. The functions in the Palevino space are C infinite, and what you have, okay, all my numerical constants from now on I will not take care of. Okay, they are one somehow. But this is just, in the L2 case, it's just a reformulation of a direct consequence of Parseval. And you can, even in the Palevino space, then you can use it for higher order derivatives. And it even characterizes, in this case, the Palevino space. The Palevino space PW2, the L2 Palevino space is precisely the one when you put K, here you have omega K, which is also a way to define Palevino spaces in other contexts. If you have some sort of spectral decomposition, you could say the Palevino space is the one where the functions behave this way. Something that looks like this. Okay, that's one. And then, okay, that's why I'm talking about this. Sampling is in the title of the conference, so that's the only place where I use sampling in my work. So you have Shannon, Whittaker, Koltelnikov, Cauchy, blah, 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 and about 50 names that you can associate to it. I call it Shannon sampling. Apologies for all the others. Shannon sampling is one of the key features, The one we teach is usually this. I think that one is in. So we have the sinc function, sine t over t, t omega t minus k. Okay, that one is taught in all courses. And easy to prove. Let me just recall how you prove it. You go to the Fourier side, and then you say this function is it's this function, okay, because of the support property, and then you say, okay, this function now I just look at it at minus omega omega, so it's, I can write it's 2 omega periodic Fourier series. Consider it not as a function on the set, but as a piece of a periodic function. You write its Fourier series, you plug it in, the Fourier series is L2 convergent, you write Fourier inversion, and that's it. And you get, then you compute what the Fourier coefficients are in terms of the function, and by Fourier inversion it's this. So everybody knows this proof. It's saying that and I would like to advocate that. Yeah, sorry. Nobody knows that. Okay, so that's Shannon sampling. That's how we teach it usually. And then those that teach it in signal processing say, oh, there are many bad things happening. And in particular, if you add L infinity noise, this thing diverges. So what you do is, oh, there's oversampling, meaning I slightly enlarge this. What makes this formula bad is that in the inversion of the Fourier transform, the characteristic function has a discontinuity. So when you invert it, you have only a 1 over x decrease at the best. Okay? If you take something like this that is smooth, then when you invert it, you get much more decay. So what is usually done, and I think that's a bad idea, is to take it C infinite. The only problem is that the Fourier transform, if anybody here knows a C infinite function with compact support whose Fourier transform is explicitly known, I would be very happy. That is unfortunately none. But you don't need that much. For a given application, it's enough to have a given decay in 1 over k to something, 1 over x to something. So the only thing you need is to do, I think, to spline. You just enlarge a little bit and you convolve sufficiently enough with the characteristic function of a one small interval, and then you get the decay you want. It's a much better way to do. And what you get in this case is something like this. So you start by enlarging a little bit. So that's why it's called oversampling. You need more samples. And then if you do what I just said, you're adding something like this. So there's a little parameter that depends on epsilon and n that I will not detail here. What is important is that you get the decay you want. And here you have sinc omega t minus. But there's a much better way to, yes?
Just short question, the Shannon sampling. Where is x on the right-hand side?
The x is t.
Okay.
Okay, I'm one-dimensional. I should stick to yes time usually. Okay, there's a better way of doing this. And if you learn something from this course, it should be this, from this talk, is that if I look at I take an alpha less than epsilon, that will be my parameter. If I take this function, this function is in the Palevina space. This Palevina space, because this on the Fourier side is just a translation. It's just a translation. So e to the I alpha k 2 omega plus epsilon, and my usual thing. Okay, so I have this. That is just the usual Shannon sampling. Plug that in here. And average with respect to alpha. This is unchanged. And if I average this with respect to alpha, I get a thing. Okay, so that is my order 1. And if you want a higher order, you take e to the alpha 1 t, e to the alpha 2 t with alpha 1, alpha 2 less than epsilon over 2, and you average with respect to alpha 1, alpha 2. It gives you a square here, epsilon over 2. If you want, what do you gain? Each time you do this, you get a 1 over k decay. So you make the formula converge much faster. Okay, so oversampling is very easy to obtain this way. It's much better. Okay, now, crash course, who knows what model sets are? Model spaces are. Nobody? Well, that's perfectly fine, me neither. So that's the good news. It's very easy. Model spaces is a family of spaces of entire functions that extend the concept of Palevina spaces. And I will explain in a second why. One of the big experts is Anton Donoho. And basically, two things that were, there are many common features. Two common features. Bernstein's inequality is known in this model spaces. And there's an equivalent of sampling theorem through a thing called Clark points. So we have these two features. Of course, all that is on this board is absent. So we wanted to extend Donoho Logan to these model spaces. And that is precisely why we needed another proof. And why did we want to extend it? Because this thing is a classical theme in complex function spaces. It's called, mu is called what is called a Carlson measure. And Carlson measures for the Palevina space were known as those for this, which this quantity is non-negative. It's old work by Lin, but that is a quantitative statement of it. It's to say that you inject the Palevina space in L2. So the question of Carlson was for which measure mu is this possible, and this is the quantitative counterpart. Okay, it's also linked to, for those who know Logan and co-serialization, which is more or less the converse. Okay. So what we wanted is to have a proof that would extend. And I will not speak much more about model spaces. I will now give you, as time is running, so model spacing, I say just a little bit. What are model spaces? Just a crash course on them. So we start with the upper half plane, C+. It's just imaginary part of Z is non-negative. And we take functions such that if I integrate, so I look at the function f of t plus I y, I check whether this is in L2 with respect to t. I want this to be finite. And moreover, I want that it be uniformly, so when I look at L2 norms on horizontal lines, I want it to be finite and uniformly with respect to y. So this is, let me rewind it very badly. So I take holomorphic functions that satisfy this, and this is called H2 of C plus. And now what is happening is that functions like this have boundary value. And this boundary value is in L2 of R. Not minus R here. And its Fourier transform is included in 0. So there's one direction which is easy. If you have this, you have this. The other one requires more work. So if you take a function whose Fourier transform is in 0, is supported in 0 plus infinite, you can extend it holomorphically to the upper half plane. Okay, so that's H2 of C plus. You have a similar object on the disk, where it's a bit easier to introduce model spaces. And then you have, so these are the functions that are, that all negative Fourier coefficients are 0. And then you can ask how the shift, you make the shift operator act, and you look for the invariant subspaces of the shifts. And with the same thing here, and they have been characterized by Burling. They are precisely those that are of this form. So theta is, I have to also to record inner, what an inner function is. So they are holomorphic in C plus and bounded. So they have they have boundary values, and you have those that are inner are precisely, so this is the boundary value of this guy. Maybe I should call it like this, and are precisely those, okay, should be for almost all those that have modulus 1 on the real line. Okay, and then a model space is precisely H2 intersected. So you can look at this space, it's orthogonal in H2, and you intersect. So the easiest example is this one. And then K theta C, what is it? It's easy to see. You take functions, everything is on the boundary. So you take a function that is supported in 0 plus infinite. You multiply it by theta C, it will be supported in C plus infinite. I should write 2C here. This one is supported in 2C plus infinite. And now if you are orthogonal to all these functions, then you are supported before 2C. In the same time, you're in H2. So this is the set of all functions in L2 of R, such that the support of f hat is included in 0 to omega. Sorry. Omega is equal to C, as you have noticed. Okay, up to a sign, you get that out of this one. Okay, so that is the way, that is why the Paley-Wiener space is a prototype of model spaces. And if you have something for the Paley-Wiener space, you want to extend it. So now, what we're going to do is to give 2 more proofs. Well, maybe only one. One more proof of this. But with bad constants. So proof 2 of Donoho Logan. Using Bernstein. So what I said is that Bernstein's inequality works here. Well, it depends on the theta. One has to be a little bit careful to make it work. What you really need for this proof is theta prime bounded. There are some restrictions on the inner function. So in this case, theta prime is just IC theta C. So when you take its modulus, it's IC, so it's bounded. But there are marginal ones for which this works. And it is just based on Bernstein's inequality, which is easy to obtain. And maybe you get all of it. We'll get out a little exercise for your students. So what I say is that I will do this for C equals 4. And it's based on a very simple lemma. You take f in L2 such that its derivative is in L2, so usual derivative or weak derivative. Doesn't really change much. You call ik the interval k delta k plus 1 delta. And you take tk any point in ik. Then you have the following lemma. The sum over k of f of tk. So I leave you as an exercise. It works also for LP. This is less than delta to the 1/2 f2 plus delta to the minus 1/2 f prime 2. And this is very easy. The only thing that you do is this thing here. This is 1 over delta sum of the integral of ik f of tk squared t. It's a stupid way of writing it. Yeah, it's enough. One proof. Okay, you have this. And what you do, you say that this is the L2 norm of the function that is piecewise constant on each ik's value, this, and you compare it to the normal function f. And so you introduce it and replace it. So one gives you this. Better this way. This is the first term, and the other term is then sum over k. So it's still a 1 over delta integral of f of t minus f of tk squared t to the 1/2. This is integration over ik. This thing here is integral from t to tk, tk to t of f prime of t, f prime of s ds, Cauchy-Schwarz and Fubini, and you conclude. Okay, and once you have this, you should be able in 1 minute, in 49 seconds. Well, you just write your integral of f of t du as a sum of integrals of ik f of t squared du. this one, you just bound it like this, and then this is less than f of tk squared, measure of ik, which is less than the soup of measure of x. Because ik is one of those intervals. And that's it. You just get then sum of the f of tk, you apply the lemma, and then you play around with the delta to optimize. Okay, and I'm 25 seconds late, so it's time to stop.
Thank you. Any questions? Remarks about comments?
So L1 version of Donoho Logan is also known, right?
Sorry?
L1.
There's also an L1 version, and there has been a recent result by for higher dimensions. I will find Hussein and Littmann. Littmann, yeah. Have a nice for the L1 version. Okay. We also have an L1 version in the model space. You can also define model spaces in L1. That trick works for P between 1 and infinity. We also have a proof with oversampling. That should be your questions. That is more complicated, but it works. And basically, you plug in the oversampling formula and you exchange integrals. And you use the decrease, the extra decrease to bound everything. But, there is no gain over this proof because you lose in the constants. You get 500 something, so non-applicable in practice. It would mean too sparse.
Okay, any more questions?
I have a comment. Yeah? My comment would be that I would recommend to write the name of Pellegrini spaces. Yeah? Because initially I was struggling somehow to identify what it is. Was it Nevanlina? Was it Perleve? And so on.
What is in it? What the connection with Nevanlin?
Pellegrini, I mean, sounds familiar. No connection. Yeah.
Okay,
Pellegrini.
so if...
Oh, I had two British mathematicians. No, one, Paley is a British.
No.
Two, Vina.
I know, Pellegrini, I recognize it.
Oh,
Yeah.
I mentioned Dirac.
You mentioned Dirac.
I mentioned Dirac. His status is in the corridor there.
Okay, so thank you, speaker, again.